Okay, in this lesson, we're going to be talking about taking the derivatives and integrals of power series. Okay, so the sum of a power series is a function f of x, which equals sigma as n equals 0 to infinity of some rule a sub n times x minus c to the n power, whose domain is the interval of convergence of the series. We would like to be able to differentiate. We would like to be able to differentiate and integrate such functions. And the following theorem says that we can do so by differentiating or integrating each individual term in the series, just as we would for a polynomial function. This is called term-by-term differentiation and integration. All right, so here's what we're doing. All right, so we're saying if we have our power series that has a radius of convergence, r greater than 0, then the function, which is defined just like we did our other power functions, is differentiable and continuous on the interval from the center plus or minus the r value. The derivative is given by f prime equals, and then notice how each of these terms in this series here correspond to the derivatives here. All right, so the derivative of our initial term without an x in it would just be a constant. Derivative of a constant is 0, so that's not even shown. Derivative of this guy is just that coefficient. Derivative of this guy to the second power, right, 2 times that coefficient, drop the power by 1, and so on. So each of these terms are just the individual derivative pieces of each of the terms in the original function. All right, and the integral is given by same idea, the integral of each of those pieces. So if we integrate a constant, then we get that constant times our variable. Because our infinite power series are always in increasing degree order, then we're going to put our plus c at the beginning, essentially. So that constant at the beginning plus each of those terms, which are integrals of the terms in the initial. All right, note the radii of convergence of the power series for the derivative and integral are the same as f of x, but the interval of convergence may not be the same because the endpoints may or may not be included. Also notice on the right side of each of those equations that the rule on the right in the case of the derivative is just the derivative of that, and the integral again is just the integral of that rule inside of that sigma. All right, so let's look at how this is going to play out. Looking at example 7, we got 3 examples that we're going to look at. Third one's got multiple parts to it though. All right, example 7 says find a power series representation for f of x, which is 1 over parentheses 1 minus x squared, centered at x equals 0, using the fact that the integral of f of x dx equals 1 over 1 minus x plus c. Okay, so if we wanted to try to rewrite f of x as a power series, knowing what we know about power series so far, we want to relate it to the sum of an infinite geometric series, which is that initial value over 1 minus r. Well, this doesn't fit into that model. All right, the square down here kind of messes that up for the denominator. So that would not be an easy task there. But looking at the integral, all right, so the benefit of this new theorem that we've got is we can say, hey, this looks a whole lot like that. Okay, so we can just pick out our initial term here and our r value here. All right, it's even already in subtraction. And we can build our power series of our integral and then take the derivative of that to find our f of x. Okay, so let's do that. Okay, so the power series of the integral of our function starts off with a value of 1. We're just going to list the first couple of terms. We're going to multiply by x each time, so times x times x, and so on. Right, and that's just x to the n power. So that's our integral. So to get our function f of x, we want to derive it. Okay, so let's do that. So let's take the derivative of each of these terms and see what we get. That should line up with our power series for f of x. All right, so derivative of 1 is 0. Derivative of x is 1. Derivative of x squared is 2x. 3x squared, and so on and so forth. Derivative of this guy would just be n times x to the n minus 1 for our rule there. All right, so this will work for values of n at least 0. And this will be fine, but typically we don't leave a series with a 0 term in it. All right, so we're just going to chop that off, and we're going to start with our 1. Because again, that 0 is not going to change the sum of our series. It's going to have the same rule, but we're just going to say we're going to start for n values at least 1. All right, and that'll be the power series that represents our f of x centered at x equals 0. Love it. All right, next up, example 8. Says find a power series representation for f of x equals natural log of 1 minus x centered at x equals 0, given that f prime of x equals the opposite of 1 over 1 minus x. Okay, so same deal here. This in no way looks like our first term over 1 minus r. So we can't go straight to that for straight to our power series for our f of x. So let's look at our derivative, f prime of x. We can just rewrite that as the negative 1 up top so that we keep that subtraction in the denominator. All right, so that means that our our initial value is going to be negative 1, and our r value, we're subtracting x, is just going to be x again. Okay, so let's build our series from that. Okay, initial term is negative 1. Let's see, I think I'm going to need some more space. So let me, cool. Let me just mess it all up. No, let's start up here. All right, so negative 1. Again, this is our f prime. We're multiplying by x each time, so we're not going to change the sign. It's going to be subtraction all the way out. So minus x multiplying by x, x squared, x cubed, and so on. Right, so that's going to be a rule of negative 1 is our initial times x to the n. Okay, but that's our f prime. So to get from our derivative, which we've got, to our original, we want to take the antiderivative. All right, so we want to integrate. So let's find that. All right, so to get f of x, that could be a new thing. Get f of x, gif of x. Let's not. All right, to get f of x, we want to integrate what we just got, which was f prime of x, power series for f prime of x. All right, so let's do that down here. All right, so integrating each term. Again, same as last time. We want to include a c at the beginning, since we're going in increasing degree order. And we're going to get negative x from there. Integrate x. We're going to get a minus 1/2. Raise that power. Minus 1/3. Raise that power. And this guy here is going to be -1/4, raise the power. And again, if we integrated that rule there, we would still have that -1. We would have x to the 1 bigger power and dividing by that 1 bigger power. All right, n plus 1. All right, that lines up. All right, so now we've got that c in there. We don't want to leave that c in there. We want not a general function. We want this exact function here. So we're told that it's centered at x equals 0. So let's take that. Let's see if we got some space up here. And if we plug in 0 into our function, then we're going to get the natural log of 1 minus 0, which is just 1. Well, the natural log of 1, e to what power gives you 1, is just 0. All right, so we know that our function has got to be 0 if we plug in 0. If we plugged in 0 into each of these x's in our new power series that we just got, then all we're going to be left with is our constant. So our constant has to be 0. Our constant has to equal that value right there. Okay, let me jot that down. So centered at 0. Plug in 0 for x. And let's see what we get. All right, so that just makes that 0. So we're just left with opposite of x minus 1/2 x squared, and so on. All right, and again, this is for n values at least 0. All right, so we got our power series representation. That's going to be for our function f of x there. All right, one left. Example number 9. Okay, it says let f of x, let f be the function given by f of x equals 2x over 1 plus x squared. Okay, so we got another rational function there. A says write the first 4 non-zero terms in the general term of this series for f about x equals 0. Okay, let's do it. Okay, first 4 non-zero terms. So we're plugging in values. What does this say? Starting at 0. So can we rewrite this as a power series? Sure. We've got our a value, which is going to be 2x. And then if we think about this as minus the opposite, so that's 2x over 1 minus the opposite of x squared. Then our r value is the opposite of x squared. All right, so let's come up with our series from there. So initial term is 2x. We're multiplying by negative x squared every time, so that means we're going to alternate. So minus, got to have that 2 there. Two times x squared times x is x cubed, plus 2 times 2 is, no, we're not multiplying by 2, we're multiplying by negative, so we changed our sign. 2 is going to stay. We're going to increase our exponent by 2 every time. Let's do one more. They ask us for 4 non-zero terms. I'm going to go x to the 7th. All right, plus, minus, and so on and so forth. And our rule for that, we've got our initial value, if we think about it as a geometric sequence or series rule, times our r value raised to the nth power. Okay, or a more differentiable or integrable rule would be to pull out that alternator pull out that coefficient, which is 2 every time, and we're just going to have, looking at that rule, x to the 2n plus 1 if we're saying n starts at 0, which we are. Okay, same rule, two different forms. But again, if this follows from the last couple examples and what we're talking about in this section, then we might need to look at what happens when we take the derivative or the integral of that rule, see if it lines up. So part B, does the series found in part A, when evaluated at x equals 1, converge to f of 1, explain why or why not? All right, so our series which was as n equals 0 up to infinity, the sum of all the terms, let's use that last rule, -1 to the n times 2 times x to the 2n plus 1. Okay, and it says evaluated at x equals 1. Okay, so for x equals 1, then if we plug that in, then as n equals 0 up to infinity, if we plug 1 into here, then we're going to get 1 to the 2n plus 1. Well, 1 to any power is just 1. So we're really just left with all of this. Okay, so opposite of 1 to the n times 2. All right, so we want to find, what does it say? Does it converge? So we want to test it, see if it is converging or diverging. So going back to our tests for convergence, looking at what type of a rule we've got. So we've got an alternator in here. All right, so this is going to be an alternating series. So let's pull out the alternator and see if we can evaluate for the limit as n approaches infinity of what's left. So the limit as n approaches infinity of 2, well, there's nowhere to plug in an n, so that just equals 2. That does not equal 0. So we can't technically show that it's converging by alternating series. So this is essentially the nth term rule. So boom, this is going to diverge if we keep adding 2's. Then it diverges by nth term test. So that means to answer our question that we're asked in the problem, does it, when evaluated x equals 1, converge to f of 1? Nope, it diverges. I'm going to need this space over here. So our answer, no. Series does not converge to f of 1 at x equals 1. All right. Part C says the derivative of natural log of 1 plus x squared is 2x over 1 plus x squared. Write the first 4 terms of the series for natural log of 1 plus x squared about x equals 0. All right, so let's integrate our power series that we have up here, since we're told that the derivative of the natural log is 2x over 1 plus x squared. That's our f of x. All right, so if we got that derivative, let's find that antiderivative of what we already have. Okay, so that's going to be of that series that we have above. I'm just copying this down from what we found in part A, right up there. All right, because again, remember our theorem that we just said, that we just looked at in our box on our previous page, said we can take, if we have a function that can be written as a power series, then we can take the derivative of each of the terms to find the derivative of our function, or we can integrate each of our terms to find the antiderivative of our function. All right, and that's what we're going to do here. Find the integral, the antiderivative of each of these terms, and that'll give us the first 4 terms for natural log of 1 plus x squared. All right, so this guy's going to be x squared, 1/2 x to the 4th, and so on. All right, those are the first 4 terms, and then if we needed more, we could find more of the original and antiderive each one. All right, last one, part D, says use a series found in part C, what we just found, to find a rational number A, or the absolute value of A minus natural log of 5/4 is less than 1 over 100. Justify your answer. All right, so we just took a left turn. So we said, all right, so to translate what this problem is asking, when it says a rational number A, what they're really looking for is some kind of a approximation. Okay, find an approximation of the natural log of 5/4 such that the error, this is our error here, all right, that should kind of smell like the error tests we did when we first started talking about these power series. So our approximation minus this actual, which is kind of telling us what we're trying to approximate. We're trying to approximate natural log of 5/4. But we want that error to be less than 1/100th. Okay, so remember, if we look at the partial sums of our power series representation of our function, then each of those partial sums is an approximation of our function. The more we put in, the better our approximation is, the closer to the actual it is. And that term after that partial sum, that next term, tells us what our error is. All right, so we're going to need to keep our eyes out for this value of one of our terms, and then we're going to add up the terms before that to find our approximation. Okay, so we've got a plan. All right, so we're looking for an approximation for natural log of 5/4. So we need to make that work for our function, which is what we just found was natural log of 1 plus x squared. Ooh, come back. Okay, so we're using our function natural log of 1 plus x squared, so we need to kind of make these mesh together. So to make it look like this rule here, 5/4 is 1 plus x squared, so that's the same thing as 1 plus 1/4, right? 5/4 is the same thing as 1 plus 1/4. And again, we want this to be squared so we can find out what that x value is. So we're going to rewrite that as natural log of 1 plus square root of 4 is 2, square root of 1 is 1. So that's the same thing as 1/2 squared. Okay, so all those are the same thing. We just need to rewrite what we're asked to approximate in terms of this function so that we can pull out this x. So now we know that our x value is 1/2. Change color here. Okay, so now let's evaluate. Let's plug in that 1/2 into our series and see when we get to a point where we've got a value less than 1 over 100. All right, so plugging in 1/2 here, we get 1/2 squared. That's the same thing as 1/4. Next up, we've got plugging in a 1/2 here. So 1/2 to the 4th. Now let me write it out here. 1/2 times 1/2 to the 4th power. Evaluating that is 1/32. So far we're still bigger than this 1/100. All right, we're alternating plus 1/3 times 1/2 to the 4th power. No, to the 6th power. All right, that's going to change things. Okay, so to the 6th power, 2 to the 6th power is, what is it, 64? 64 times 3 is definitely going to be bigger than 100. All right, so this is 1/192. All right, so boom. So we've hit a point where this 1/192 is now less than 1/100. Okay, so this tells us, stop, this is going to be our error, and we want to just include this part right here as our approximation A. All right, so this is our A here. Okay, so what is that? 1/4 minus 1/32. Let's see, 4 goes into 32 8 times, so that's going to be 8 minus 1 out of 32. So 7/32, that is our A value. Okay, we were asked to find a rational number A, and that is our approximation for it. So 7/32 is our approximation for the natural log of 5/4. It should be within 1/100ths of a unit of the actual natural log of 5/4. I challenge you to plug it in your calculator and evaluate it and see if that is true. All right, and that's it. So big idea from this section was that if we have a function represented as a power series, and we're either given or we need to find the derivative or the antiderivative, we can do that of each term in that series instead of the function rule itself.